Hi guys. Okay, so I've got another example of the Frobenius method. And look, if today was confusing, try not to be hard on yourself. This is opaque stuff. And I think it would be a little bit easier if we were in person. There's something about trying to watch this on a screen that's just not the same as being there. But I'll do what I can. And so let me look at, or let's look at a general problem. So again, just to remind yourself, we're going to look at the case where, let's say y is equal to, we'll use s this time, x to the s times the sum from n equals 0 to infinity of a sub n x to the n. And so our solution, our proposed solution for the differential equation is going to be a sub n times x to the n plus s. Okay, that's our starting point. Right? And the reason why we do this, again, two reasons. Right? One is that we might be able to find both linearly independent solutions, and the other is the other way of doing this with power series doesn't capture things like solutions that have negative powers of x in the power expansion. Okay, so let's look at just this example: x squared times y double prime plus 4xy prime plus x squared plus 2 times y equals 0. All right, ordinarily we'd look at that and how the hell do you solve something like this, right? This is not anything that looks like it's amenable to any of the forms that we've looked at before. So let's look at if we use our expansion, we can write that y is equal to a naught times x to the s plus a1 times x to the s plus 1 plus a2 x to the s plus 2 and so on, or the sum from n equals 0 to infinity of a sub n x to the n plus s. Right? That's just the definition of our solution. Y prime is going to be s times a naught times x to the s minus 1 plus s plus 1 times a1 times x to the s plus s plus 2 times a2 times x to the s plus 1 and so on, and that'll equal the sum from n equals 0 to infinity of n plus s times a sub n times x to the n plus s minus 1. And then finally, y double prime is going to be s times s minus 1, a naught x to the s minus 2, plus, and you get the idea, this will be equal to the sum from n equals 0 to infinity of n plus s times n plus s minus 1 times a sub n times x to the n plus s minus 2. All of this is generally true, right? This is just defining what y prime, and y double prime is for our proposed solution using the Frobenius method. Okay, so now, and I think that what might be useful is doing the kind of table that I had before in the other problem, except now we're going to use this to try and find the indicial equations. So instead I'm going to write down here on this will be the different terms, and then here will be this way, and then powers of x will be going across that way. Right? So if we remember our equation up here, right, we have x squared y double prime, we have 4x y prime, we have x squared y and we have 2y in this sort of dummy problem, right? And then we want to consider xs, xs plus 1, xs plus 2, all the way up to x to the n plus s. Okay. So if we look at our x to the s power, right? That's when in our sums n is equal to 0 up here for that first, whenever we have y by itself, right? So we can go through these, and if you collect terms, you'll see that s times s minus 1 a naught, 4s a naught, this term has nothing, and this term is 2a naught. Okay? In other words, if we isolate, when we start doing the sums for this equation up here, right, x to the s has these set of coefficients. X to the s plus 1 has s plus 1 times s times a1, 4s plus 1 times a1, again nothing here, and then 2a1. And x to the s plus 2 will have s plus 2 times s plus 1 times a2. This will be 4s plus 2, a2. Now we have an a naught here, and this will be 2a2. And then in general, what we'll have is n plus s minus 1 times a sub n, 4n plus s times a sub n minus 2, and 2 times a sub n. So what do we do with this table? Let's remember what we're doing here. N is our index over the sum, right? S, in this case, is the power, right, that ultimately gives us the indicial relation, right? So each one of these columns have to sum to 0, right? So we have to have, for example, s, what we have, for example, is s times s minus 1 times a naught plus 4s a naught plus 2a naught is equal to 0. S plus 1 times s times a1, oops, yep, plus 4s plus 1 a1 plus 2a1 is equal to 0, and so on. Right? So the total coefficients for each power must be equal to 0. If we look at this first equation, right, we can expand this out, and we get s squared plus 3s plus 2 has to be equal to 0. And that's because we're assuming that a naught is non-zero. We're not assuming a trivial solution, right? That means that s is equal to minus 2 or s is equal to minus 1. Okay? This is our indicial equation. Those are our two possibilities, and in fact, what it means is if we can solve this equation for the value of s minus 2 and s minus 1, we've found both linearly independent solutions. What this means is that our power series, right, is equal to some constant times x to the, if we're doing over, not s, but n, sorry, over n, it's n to the minus 2 or n to the minus 1, right? So what do we do with this? Ultimately, we want to find a way to relate the coefficients to each other. We can solve these for each different case. So let's look for s equals 1. I'll do the s equals minus 1 case, and then I want you to try the s minus 2 case. If you have some problems, we can go over that too. Maybe I'll post the solution later on this week. Okay. So if we start with s equals minus 1, we know that the coefficient of x to the s plus 1 in our table above gives a1 equal to 0. And we can keep moving on to solve for these different equations. Remember, we are doing all of this up here based on this idea, these substitutions, and the fact that these have to be in columns add to 0. Right? So now we have the choices of minus 2 or minus 1. Okay, so for if we look at the general case, so the last column in the table above, for s equals minus 1, what we get is a sub n times n minus 1 times n plus 2 is equal to minus a to sub n minus 2. Okay, you should convince yourself that that is correct. Look at the column above and set s equal to minus 1, and you should be able to collect terms and show that this is correct for those two different indices. So that means that a sub n is equal to minus a sub n minus 2 over n times n plus 1. Right? And this is true for n greater than or equal to 2. Why? I'll let you think about that, but if you look at the table, the answer should become a little bit clearer. Okay? Since a sub 1 is equal to 0, that means that all odd terms are 0 for s equals minus 1. That may not be the case for s equals minus 2, right? So that means that for even a's, we start plugging in values. A sub 2 is equal to minus a naught over 3 factorial. A sub 4 is equal to a naught over 5 factorial. A sub 6 is equal to minus a naught over 7 factorial, and so on. So that means that the solution, we'll say the y sub minus 1 solution of this differential equation is a naught x to the minus 1 minus a naught over 3 factorial x plus a naught over 5 factorial x cubed minus plus and so on. Or, finally, y sub minus 1 of x is equal to a naught times x to the minus 2 times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. But we know what that is. Aha! Y sub minus 1 of x is equal to a naught sine of x over x squared. And you can check by substitution that this is the actual solution. Okay. We're lucky in that this created a solution that had a closed form. That won't always be the case, but that is what we're always driving for if it's possible. So look over this example again, look over the examples in lecture again, and remember that the idea is we're going to write y as x to the n plus some indicial power. We're going to solve for the coefficients to find what are the two roots of that power. Right? In this case, it was -1 and -2. That's our indicial equation. And then from that, we'll find the recurrence relation. How does one coefficient relate to the coefficient prior to it or two steps behind it? And then once we know that, what's the series expansion? Does it have a closed form? In this case, it did. In the Legendre equations, it doesn't necessarily, right? It just has an expansion. All right, so I hope this is helpful. Hang in there, guys. You're doing great. I'm really proud of the work that this class is doing. And I'll be around if you have questions. Okay? All right. See you later.